Welcome to a harmonics session. This is our first class on harmonics. We're going to have two classes on harmonics, and then we're going to have a couple classes on batteries. So uh, hopefully you can get a basic understanding of what's going on in both these topics. So this is different. It's going to be a YouTube presentation, and you'll be able to watch it on your own time. I do want you to still turn in an email to me letting me know that you have watched this presentation so I can keep attendance records. So let's talk about harmonics. This basic overview, we're going to talk about what are harmonics, what can cause harmonics, uh, and then we're going to talk about the effects of harmonics on electrical systems. And then we're going to talk about how some ways that we can control those harmonics. And so that'll be in next week's lesson. But basically, I have a waveform here, and you can see some various waveforms here. And we're going to talk about each one of these topics separately in just a little bit. But we have a fundamental frequency, which typically in our world is 60 hertz. Then we have some other harmonics that ride along that. In this case, we've written a third harmonic, and we haven't discussed that very much or at all, and we'll discuss that further. But this is the green waveform. This is what we've added to that green waveform. And then effectively, what we end up with is this reddish brown type waveform, which looks nothing like the perfect sinusoidal waveform that we really want in our world. And because of that, we end up with some various problems on our electrical systems. Some of them are quite serious. So let's look at the explanation of harmonics. A resistive circuit, the current. Okay, we go back to Ohm's law here. We have current voltage equals current times resistance. So in that resistive circuit, and also current equals voltage divided by resistance, Ohm's law. In that resistance circuit, the voltage is applied to it. If the voltage is a sine wave, the current's a sine wave. Okay, so it replicates that. That's called a linear relationship. I have a very basic equation that's linear, and my output is very linear with the input. So here are mathematical equations for voltage and current. We don't need to have all the math there, but we can understand that we've got a voltage input here, we've got a current input, and we've got a ratio between those two that is always linear. That's very important for us to understand. We want linear aspects in our world. Now, with respect to that, everything in our world is not just purely resistive. Everything in our world is not linear. So you can see how this waveform, it looks the same shape, okay, and follows the same pattern. It's a difference in magnitude, but that's just a linear relationship. Now, if we look at other waveforms, in a circuit where the voltage and the current relationship is not expressed by a simple circuit or a simple equation like voltage equals current times resistance. In other words, it's not proportional to each other. Those waveforms or those outputs, the waveforms that we see, they're not sinusoidal. Okay, so it's a non-sinusoidal waveform, or we could call it a very complex waveform because if we look at the waveforms here, this is what we wanted or close to it. It's almost a sinusoid, a perfect sinusoid. That's what I want in my world. But look what I've got. It doesn't even resemble what I would expect for it to do. And it's not a linear relationship. It's not a simple equation that I can write. That's a very complex waveform that I've got to deal with. Unfortunately, that's the type of waveforms that we see from time to time on electrical systems that we have to work with. And we have customers that call us all the time concerning themselves with harmonics issues. A lot of times they don't even understand that they have harmonics issues. They'll just say, you know, my variable speed drive keeps tripping off, or I keep blowing fuses in my power factor correction capacitor bank. Those are kind of symptoms of these harmonics, but we're going to have to get to understanding exactly what's going on there. Now, if I look at our world, the world as I want it, uh, I like this fundamental frequency. And in my world, that fundamental frequency is what? 60 hertz. 60 cycles per second. That's what I want. That's what I'm going to send. That's what the utility is going to provide to our customers is a sinusoidal waveform. That's the supply. That's the frequency we want. And it looks exactly like this, where it peaks at 90 degrees. It crosses the zero crossing at 180 degrees. It peaks negatively at 270 degrees, and it back across at zero. And again, we can look at that, and we can look at one cycle of a waveform. We have 60 cycles per second, okay? 60 cycles per second. That's where we get our hertz, 60 cycles per second. So if I look at how much I have in 1 second, 1 divided by 60 is 16.67 milliseconds. So every 16.67 milliseconds, okay, or 0.0166 seconds, that is 360 degrees. So every 16 milliseconds, I repeat that waveform. So that's what I'm looking for. That's what I'm expecting. That's the world that I want to deal with. That's the world I do all my calculations in. That's the world that I took all my electrical theory in when I was in school. Now, that's the fundamental frequency. Now, if I look at this fundamental frequency, and I'm looking at complex waveforms now, because right here's the world I want, a fundamental frequency going back and forth, just exactly like I would expect for it to. And that's going very well. And my output waveform is right here. Look, they match each other, okay? But now I have some second harmonic. So if this is 60 hertz, then the second harmonic would be 120 hertz, twice that. So you can see that for every time, I have 2 complete cycles for the same time frame, okay? So it's going up and down twice for one time period, which in my world is 16.67 milliseconds. So this is what's happening, going twice as fast. So I have the red waveform. That is an indication of the output. The purple here is what my sinusoidal 60 hertz, my fundamental is. The green waveform is what my second harmonic is. And you can see if I have enough second harmonic, how I really distort the output waveform. This is what I want, but this is what I've got. Well, let's look at the third harmonic. So in this case, in my world, third harmonic is 3 times 60, which would be 180 hertz. So at 180 hertz, I see that, you know what? I have 3 waveforms through that same 16.67 milliseconds of time frame. So again, I go back to purple. There's my fundamental frequency. There's my harmonic. There's my third. Now the output waveform looks like a camel, double hump camel on both sides. Certainly not like anything that I would want to see in my world. And I can do the same for the fourth harmonic. 4 times 60 would be 240 hertz, and that would be the diagram here. But you can see as I add these harmonics onto my existing signal that my output doesn't look like the waveform I want. And that's the whole problem that I'm having with harmonics. It's more than just looking poorly. It's actually impacting what's going on in my world. Now, classifications by names, you can go through this. Second harmonic is 2 times 60 hertz, 120 hertz. Third harmonic is 3 times 60 hertz, which is that 180 hertz. Fourth harmonic is 240 hertz. Okay, fifth harmonic is 300 hertz. And you can go on and on and on and figure out the different harmonics. Now, typically in our world, when it gets above the 9th, 10th, 11th harmonic, it's pretty small quantities there. So we need to take another little trip down another path. Positive, negative, and zero sequence voltages and currents. Okay. Now, in my world, I like this little guy. He's looking here And this is my positive sequence world. This is the world that I want to live in. This is my waveform that I've always got. And that's a balanced system. So in the positive world, as I'm looking, I can see A phase come by, and then B phase rotates by, and C phase rotates by. And that's just the little world I've got. And that's balanced, a balanced three-phase system. Okay. And then I have this area where I call negative sequence. Is anytime I have an unbalance, no ground fault, but just an unbalance, I have these same currents, but now what are they doing? It's rotating A, C, B, not A, B, C, it's A, C, B. And then for unbalanced conditions where I actually have ground fault going, I have all three currents in phase uh, rotating the same direction, okay? So on various harmonics, I see things happen. So for fourth, seventh, and 10th harmonics, I see positive currents. It, the waveforms add, but there's really not any unbalance of the system, but the waveforms add. And so I will see currents there that create overheating in motors, in power lines, and in transformers. Okay, so it just could be some overheating there. Sometimes negligible, but sometimes not so negligible. For second, fifth, and eighth harmonics, that looks like an unbalanced situation. And so current is now flowing between phases because I have an unbalance. So if the current's flowing between phases and not going where it's supposed to be, then my magnetic field in a transformer or a motor uh, would be less. And so I'll have less mechanical torque in my induction motors. So I might not be able to have as much torque. And if I'm trying to create the same amount of torque, then I'll have more slip, and I can create some additional heating inside there. And in the third, sixth, and ninth harmonics, those are called zero sequence harmonics. Uh, it appears that I've got an unbalance, and now the unbalance is returning back into neutral. And those are areas that really are concerns for us. So let's look to see what's going on there. So let's look at those triple harmonics, third and ninth, what we typically see. So here's our waveform, A, B, and C phase. And we need to understand that they're 120 degrees out of phase. So here they are. There's A phase waveform. That's what I want. There's B phase. That's what I want. And there's C phase. That's what I want. There's C phase. That's what I want. That's my typical waveform. But now I have third harmonics. So you see the waveforms, third harmonics right here? That's the third. That's the third. That's the third. If you look, all those waveforms add up. And so even though I have balanced systems, I mean, you understand that if I have a Y system, Y connected system, A phase, B phase, C phase, and out here I have it all returning back to the neutral. There's my neutral, my star point, that in theory, that this current in the neutral should be 0 amps, because the sum of the currents, all the phases, should be 0. And that's 0 in a balanced system. But look here, even though I've got a balanced system with this triplet harmonics, this third harmonics, look at the instantaneous values. Like you can see on A phase right here. If I add this with this part, with this part, C phase, all at the same time, if I add those all up, they would add up to 0. At any given point, the three fundamental frequencies, if I add them all three up, they would add up to 0. But look here. If I add this portion of the third, and this portion of the third, and this portion of the third, they don't add up to zero. They actually add up to 300% of the third harmonic. Okay, so typically I don't want neutral current uh, to have anything in it, but the third harmonic is 300% of the phase current. So they add up, they don't cancel each other out. And that's a real problem. And that causes a lot of overheating, a lot of excess current. That causes UPSs to turn off. That does cause fuses in capacitor banks, power factor capacitor banks to blow. So, what are some of those causes for harmonics? Well, some of the places we work, steel mills, they have arc furnaces. Okay. It's just like a lightning strike. That's not 60 cycles. It's just like a one big rush of current and one big dip of voltage. Okay. We have other discharge devices like fluorescent lamps. They do the same thing. Uh, Not to the same magnitude, but if we have enough fluorescent lamps, we can do that. Resistance welders. I can have welders as they come on. That's not a good sinusoidal impact to my system. They're messing that system up. Magnetic cores. Anything that requires third harmonics to excite the current can be a problem. Synchronous machines, if they try to overexcite those synchronous machines in order to provide power factor correction, they can create fifth and seventh harmonics. Anytime I have variable frequency drives, variable speed drives, they vary the speed by varying the frequency. Matter of fact, back in the old days, we called them variable frequency drives. Those things will change the frequency of our 60 hertz because that's a problem. Solid state switches, heating and light intensity, they will create harmonics on our system. Switched mode power supplies. Okay, we talked today about we buy energy efficient devices. And I we have laptops, we have computers, we have TVs that we call energy efficient. Well, they do that by switching solid state wise inside. Um, Switch mode power supplies for PC and TV. So they're creating energy efficiency, but by the same time, they're creating harmonics on our systems. If we have high voltage DC transmission, uh, for instance, if we go from the East Coast of the United States to the West Coast, the transmission grid's all connected together, but it's really hard to get the frequency. It was years ago when we connected the East Coast to the West Coast, get across the Rocky Mountains because we only had like one or two transmission lines that went across there, and it could be a lot of swinging. It was hard to synchronize. So they converted the AC on one side and the AC on the other side to DC. So the interconnect between the east and the west of the Rockies was a DC interconnect. Well, guess what? Uh, that DC transmission created harmonics, okay? And then we have photovoltaic cells. Uh, we have the solar farms that we have. They have to have inverters to convert that DC to AC. There's some harmonics that are happening along that conversion as well. So if I looked at switched mode power supplies, okay, so basically I've got phase one, phase two, phase three, A, B, C. I can see that I want a DC output. Uh, I've got all these silicon controlled diodes right here, SCRs, that I'm switching on. So I'm switching on at various times so I get a nice smooth waveform out, DC waveform. But all of this switching creates another pulse. And every time I have a pulse that's adding a little harmonics, something else that's a little different on my electrical system that adds some distortion there. Now, if I look at just fluorescent lighting alone, and I look at 16.67 milliseconds, okay, right there, remember, that is one cycle. And if I look at this, look at the current. Now, no big deal. We're talking about milliamperes of current here. But if I look at the current and time, I want, didn't draw it very well. That's the waveform I want. But this is the waveform I've got. Okay, now voltage-wise, I'm trying to provide that waveform, but this is the waveform. This is where the fire the fluorescent tube, and I see a big spike there. That doesn't resemble anything like that sine wave that I wanted. It does repeat itself, but I've added some additional information on there. So it's a highly distorted current waveform. Again, very small. But if you have thousands of these fluorescent tubes in a large office building, that can be a significant portion of the electrical system. So we get into the terminology that's called total harmonic distortion, THD. So talking about total harmonic distortion, I'm going to read this out of the IEEE manual. It says that utilities typically supply voltage with less than 2% total harmonic distortion. And we'll get into some calculations in harmonic distortion in a little bit. However, the current total harmonic distortion may be very high. So utilities are watching. They're going to start hammering you pretty clearly if you're doing stuff that's going to try to increase their voltage supply, the harmonic distortion and the voltage supply. But you can do a lot of things internal that mess with the current. Now, in theory, there's an infinite supply to your company or your business or your factory or your steel mill. So in theory, you couldn't do anything to harm that. But in reality, we can impact that. And in reality, I have my own little separate electrical system that I can have lots of distortion, both voltage and current wise, on my little system. So what we're looking at is that the recommended allowable voltage harmonic distortion at the point where the building connects to the utility, this is a little bit older, 1992, is 5%, okay? So we don't want to see a voltage distortion above 5%, and really that's really pretty poorly, okay? And then we have a table, figure 5 on the next page, shows that the voltage distortion, this reaches at approximately half the building's load, has a total harmonic distortion of 55%, okay? And we're talking with current there, okay? So we need to compare voltage and current. Now we have a diagram like this, okay? This came out of the IEEE standard. Total harmonic distortion resulting from 55% and 115% current distortion. So this is really trying to tell you, it's like, okay, what happens if I have things in my system that distort the current? And that's exactly what we have. We distort the current. And that results in a distorted voltage waveform. Now, my little system here, I can mess with the current quite a bit without harming the overall electrical system. But there are limits to that. So basically, what they're saying is that if 55%, here we could read the subtitle here, the voltage is theoretically exceeded when approximately 47% of the total load in a building has 55% total harmonic current distortion, or when 26% of the load has 115% harmonic distortion. So basically, if I come here and I look at the actual load and percent of total load, if my total load has a harmonic distortion of 55% and 47% of that building has that kind of distortion, then I will exceed my IEEE voltage limit. If I have a total harmonic distortion of 115%, then it only takes about what, 25, 26% of the total load before I exceed that limit. So that's a little chart that will give you some ideas of exactly what's going on there. But we don't have a feel right now for what all that means when it comes to total harmonic distortion. So basically, here's the definition. Here's the formula, okay? So if I look at total harmonic distortion, okay, and there are two ways to look at it. There's a way the ballast manufacturers and other places look at it, and here's the other way to look at it. Two different calculations for total harmonic distortion, and they don't vary a lot. But basically, I'm summing up the squares of all the harmonics for the various frequencies. Okay, so there's second harmonic, there's third harmonic, there's fourth harmonic, and I'm summing them up all across all the harmonics I have, and I'm dividing that by the square root of my fundamental. Okay, and I convert that to percentage. Okay, now that's one way. And then the American ANSI standard looks at it this way, and they sum up all the frequencies down here, and they include all the other frequencies, not just the harmonics. So if I look at that, if I look at the total harmonic distortion reported by manufacturers according to IEEE, these would be values that I could receive. If I do the calculation as the Canadians do, these are the values I'd get. They don't show quite as badly. You see the big differences when it gets up very, very high. So we can see that we can actually calculate total harmonic distortion, and we can understand where that calculation is coming from. Now, what does that mean? Well, if I look at typical devices that we have on the system, okay, if I look at typical devices that we have on the system, like compact fluorescent lighting, okay, a 13-watt quad tube fluorescent fixtures, okay, with magnetic ballasts. There's my watts, there's my power factor. Man, the power factor sucks because I'm wanting that up there pretty close. But look at my harmonic distortion, 13%. So if I have an electronic ballast, look what happens. Okay, now I've got an electronic ballast. My total harmonic distortion is 153% with respect to current. So I've done some things here to save energy by having the electronic ballast, but I've really sucked at doing some things with regard to harmonic distortion. Then I can see some things for different type lamps that I can use, T12, T8 lamps, those sorts of things. I can see those are all relatively low total harmonic distortions and much better power factors. Okay, so that's good. High intensity discharge lighting systems, power factors are good. Harmonic distortion, not horrible, as long as the whole system's not made up there. Incandescent lighting, my old incandescent light bulbs, okay. Power factor, unity power factor, but look at the watts, okay. Harmonic distortion, not much, but looky here what's happening. The lights here, I had 16 watts there, 101 watts here. So I can start to see that, with the energy efficiencies, then I have some issues with harmonics. Finally, get down here to some things that we talk about on a routine basis. A desktop computer with a monitor, harmonics about 139% with respect to current. Color monitored for the desktop computer, 138%. A laser printer, 224%. So those items that we see on a routine basis are really, really, really impacting us with regard to the harmonics that we just throw on the system. Now, little review on resonance, okay, because we have to deal with this harmonics a lot. And if you're taking some other classes, we've done some of this review too, but resonance of a tuned circuit, inductors, capacitors, is given by the equation. This is a NETA problem as well. The resonant frequency is 1 over 2 pi times the square root of LC. Pi, of course, is 3.14. 2 pi is 6.28, okay? So I can actually calculate the impedance, X sub C or X sub L, of a capacitor or an inductor based upon the frequency associated with that. But I can also find out when this X sub C, capacitive reactance, is equal to the inductive reactance. And when those two are equal to each other, that is called resonance. Okay, so we want to look just a little bit at resonance here. So if I have this basic, simple series circuit, and we're not going to go into deep deep math today on this. But on this very basic, simple circuit, if I have a resonant frequency, and I don't know what that resonant frequency is, I have the equation for that in the last slide, but whatever that frequency is, I want to say at this resonant frequency, X sub C equals X sub L. And that's the definition of resonant frequency. And it just so happens at that frequency that X sub C equals X sub L equals 4 ohms. So at that frequency, this is a 4 ohm capacitor, and this is a 4 ohm inductor. If I look at the X diagram, here's resistance, here's X sub C, and here's X sub L. So I've got 4 ohms of capacitive reactance. I've got 4 ohms of inductive reactance, plus 4, minus 4. They cancel each other out. So basically, at this resonant frequency, the resonant frequency of this simple series circuit, these two cancel each other out. So X sub C plus X sub L equals 0. It's a short circuit. And that's important to us to understand that. So at this resonant frequency, basically I can take a jumper wire from here to here and jumper it out. And so the current would flow in that circuit through the resistor like this back to the source. Effectively, there's no capacitance or inductance there. So that's series resonance. If I look at the impact there, I can see for various frequencies that various things can change. And I can look that here is a plot of the inductive reactance, which is given by the equation of 2 pi FL. I can see that as frequency increases, this impedance, inductive reactance, increases. And it's a linear relationship, okay? Now, I also know that X sub C equals 1 over 2 pi FC. So as the frequency increases, the inductive reactance goes down. But it goes down in this manner. It's not just a linear, it's an exponential function. So there we go. It goes like that. So if I look at a combination of this inductive reactance and capacitive reactance and add them together because they're in series, it looks something very similar to this. And I can find out at the resonant frequency that those two things add up, they're equal to each other. And at that resonant frequency, the total impedance of the system is simply that resistance. Okay, so that's a graphical representation of what we talked about before. And this is the impedance total given versus frequency. That would be the equation for that. So if I look at the current in this circuit, as the frequency is happening here, the minimum resistance, minimum impedance would be at resonance. So here we go. The current would look like this. At resonant frequency, the current would be maximum because the impedance is minimum. So that would be like the series resonance circuit. Now, there are effects of various parts of the system, okay? The effects, the smaller the R, the larger the current. So I can see the impacts of what happens if R gets smaller or larger. And then that impacts the peak current. But I can also see here where the width is varied by the ratio of the inductance to the capacitance. So I can change that waveform. And I'm not in the process of changing that waveform, but I'm in the process of understanding what's going on here. So at our steel mill, if I look at the Nucor Steel Yard at Crawfordsville, Indiana, they have a filter yard. And so they have what? An inductor and a capacitor in series, okay? And that inductor and capacitor in series, that is a series tuned circuit, and they have that tuned at the third harmonic. Then they also have one tuned at the what? 300 hertz, which is the fifth harmonic. Then they also have one tuned at the 420th hertz, which is the seventh harmonics, okay? So they have problems on their system that they understand that they've got what? Third, fifth, and seventh harmonics. So that third harmonic, this inductor capacitive series circuit, that would be basically a short circuit. So any third harmonic they have on their electrical system would want to go that way and would not go back out on the utility. Any fifth harmonic would tend to go this way because it would look like a short circuit. Any seventh harmonic would tend to go that way, which would look like a short circuit. So that's the steel mill's path to try to resolve questions, problems of harmonics they're creating. Now, parallel resonance, let's just suffice it to say that if X sub L equals X sub C, and we can go through the math there, but if that happens, then this combination right here of the inductance and the capacitance in parallel, that little section of the circuit, Z total there, is infinite. That becomes an open circuit. So if that happens at that resonant frequency, the total impedance of this circuit, again, is R. Current's going to flow this way. No current's going to flow here because I have basically infinite impedance there. So I have a waveform that looks like this. Now this is a waveform. This is the diagram of impedance, okay? So if this is the impedance and I were to draw frequency versus current, then my waveform for that would be like this because it's got to be the inverse of the impedance. And at the resonant frequency, I have minimum current, maximum impedance. And I can see things that would have effects on that as well. I can see that here's the value of R, which will flatten out the curve. And I can also see where my ratio of inductance over capacitance will also impact that curve. Both of them are very important to us. The Q of a circuit, Q of an inductor. No inductor is perfect. So here's my diagram of an inductor. But you know what? That's a coil of wire. So in essence, inside that little inductor is resistance, and it's called wire. So this function, this Q, is a ratio of the inductive reactance divided by the actual resistance of that circuit, okay? And so the Q of this inductor will look very similar to this. And that high Q inductor will shorten the bandwidth. It'll make it a very sharp peak bandwidth, where if I have very, very, very large resistance, then it's just going to be like a flat resistance there, or a flat bandwidth. So it has some real issues for me, has some impacts for me. So I mentioned before, this final slide in this class, mentioned before that as we look at this parallel tune circuit, it's not perfect. It's got some resistance there. I didn't want that, but that's where it is. And if it's almost a perfect resistor, so it's going to be really, really good. What happens is, you know, at resonance, this is supposed to be an open circuit, and all current flows right here. And I would have zero current flowing right there. But I have a voltage across this resistor, so I have voltage across here, and I have voltage across there. So I have current flowing through this inductor, and I have current flowing through this capacitor, but they're going opposite directions. So it'll circulate this way, it'll circulate this way. So basically the inductor feeds the current for the capacitor, and the capacitor feeds the current for the inductor. So the sum of this little loop is zero. So I truly do have zero or close to zero current flowing there, but I can have huge circulating currents coming in that capacitor inductor combination, to the point at a hospital here in Indianapolis, they had a lot of inductors. They are called chillers inside the plant, okay, for cooling and airflow and everything else. Their power factor was horrible. So they added this large capacitor bank at the utility. So here's the utility right here. So in essence, didn't see much current flowing here, but this circulating current flowing back between this inductor and this capacitor. Everything else is going on in the rest of the hospital, but this little circulating current between this chiller, inductor, and this capacitor at the resonant frequency was so high that they not only blew the fuses on the capacitor, but they had to call the fire department to put the fire out, okay? So that circulating current created by a harmonic that was a resonant harmonic created by the inductance and the capacitance of the system created havoc on their electrical. All right, so that is week 1. Week 2, we're going to talk some more about those harmonics. If you have questions, just send me an email. Be glad to try to respond to that if we can. And we'll do everything we can to try to respond. We do want you to let us know if you have questions, and I do want you to let me know that you have watched this recording. Thank you very much. Have a great week now.